So finally, we will conclude with actually looking at specific three-dimensional geometric figures to determine how do we calculate their volume or their surface area. And we're going to start with just a basic prism. Now, if you recall, a prism is going to have a specific polygon at each end and then connected with rectangular sides. I noted some in the previous video that I even have with me. The hexagonal prism, right? The box that's hexagons on both sides. Or the square prism that has squares on both ends, and again, rectangles on the sides. And they have the same general approach to finding volume. In the case of this rectangular prism that we see here, notice the base, right? If we think about the base as the bottom layer, this has 20 centimeters this way and 10 centimeters this way. So if we look at the base, the base layer as 20 centimeters by 10 centimeters, that would be 200 square centimeters. And then we have 6 layers of those. So we multiply that by the height, which is 6 centimeters, and we find out that this is 1,200 cubic centimeters. And again, we're measuring cubes when we're talking about volume. So this will be the case for every rectangular prism. If you want to find its volume, you are going to take its length times its width times its height. So the volume of any rectangular prism can be stated as length times width times height, just as we see right there. So that's if it's a rectangular prism. Now we have other prisms besides rectangular prisms. We can have triangular prisms. We approach this the same way, where we start off by looking at the base. And we find the area of the base. In this case, it's a triangle. And so to find the area of the triangle, we multiply the length times the width and then take half of that. So we take 1/2 times 3 times 3, which is equal to 9 divided by 2, or 4.5 square centimeters. That's the area of the base. That's this shaded section right there. Then we have 6 layers of those. So that's going to be multiplied by 6, which is 27 cubic centimeters. So in this case, for this specific prism, the volume was found by taking 1/2 of, we'll call this the base. Actually, what we'll do is maybe we'll call this the length and the width, and this the height. 1/2 times the length times the width times the height. And the reason we did that was because this was how we calculated the area of the base that was the triangle. So if we start to notice this sort of generalization, we can say that any prism, no matter what the shape of the base is, can be found by multiplying the area of the base times its height. And then how you calculate the area will be dependent upon what shape the area is. In our first example, we saw that it was a rectangle. So that was where the length times the width came from. In the second example, it was a triangle. So that was where the 1/2 times the length times the width came from. And again, that's going to be the case for whatever type of prism you have. So these two that we just saw were what we would call right prisms. They met at a 90-degree angle. But if you recall from a previous chapter, we also saw what we called oblique prisms. And oblique prisms are where they're not straight up and down at a 90-degree angle. They are shifted like this. And what I'm going to use to demonstrate this is actually a deck of cards. These Super Mario Brothers Uno cards. And so if we think about this deck of cards, it's got all these layers, and this is going to be the volume, right? Like if we think about this entire, this is a rectangular prism, right? So this is the volume of the deck of cards. Now, if we can take this cards, and if I can get this nice and close, and I just tilt it a little bit, to see the best way to do this. I'm just going to tilt it with my hands, and then we'll hold it like this. Noticed how it's the same deck of cards, right? But it's just been tilted at an angle. This is now not a right prism anymore. It's an oblique prism. But the volume has not changed at all. If I straighten it back out, it's still exactly the same amount of stuff. It takes up exactly the same amount of space in the world. And so the volume actually does not change. Here's another picture of what that can look like, a little more formalized, I guess. Right, so here's your stack of cards straight up and down. Here's your stack of cards skewed a little bit to the right. There's that, again, that oblique shift. So how do we find the volume of an oblique prism? The same way we find the volume of a regular prism. It's still the area of the base times the height. We just have to know the height is that altitude, right? The height is always measured moving straight up at that 90-degree angle. Now, when we want to find the surface area of a prism, when we talked about this already, I showed you the Rubik's Cube, we are just adding all of the areas of, not that one, all of the areas of all of the individual faces. We already did this a little bit. I'll scroll back up in the previous video when we were finding the surface area of this, right? So it's the sum of the surface area of a prism is the sum, add them all up, of all of the areas of the bases and the faces, right? So that's going to be the case for any type of prism. So let's move on and talk about cylinders. So what is a cylinder? Again, I have a couple cylinders with me here. Right, one was this, right? This package, right? This nice package. It's got perfect circles at the bottom and the top, and again, perfect straight up and down sides, right? 90-degree sides. Here's another example, right? This light shining in, right? So this little container, right? Perfect prism or cylinder, circles on the top, circles on the bottom, straight up and down. So we need to know how to find the volume of one of those. So let's do a little examination here. The first thing you might try, right, if you're going to try to teach this, is you might have students try to fill a prism. I keep saying that, fill a cylinder with blocks. But the problem with that is you're going to have this space on the sides, right? And so you can get a rough estimation, but you know you're going to be a little bit short. It's actually very similar to prisms. A cylinder is very similar to a prism in that if we could find the area of the base, right? If we could find the area of that circular base, then we can multiply it by its height, just like we did with our prisms. And so what I'm going to show you is I'm going to take you to a website, and I've got this link also in Blackboard. And so let's just take a moment to reflect on circles. If you want to play around with this, you can grab these little green dots and hold in with your mouse, click and drag. So what you'll see right here on this grid is a circle, and that circle has a diameter of 8 which means its radius is 4. Now, how do you find the area of a circle? Pi times the radius squared. You'll see that right here. Notice we have pi times 4 squared. But if we're going to want to find the volume of this cylinder, we are going to also multiply it by its height, just like we did with the prism. So here's where you can click and drag, and watch what happens right here in this formula. Pi times the radius squared. This is going to represent the height. So I'm going to just drag this up 1. It's not letting me drag it up 1. For some reason, it's not letting me drag it up 1. I'll drag it up 2. That's okay. The height is equal to 2. So notice how it's pi times the radius squared. Now it says times 2 because that is my height. That is equal to 32 pi, which is 200.96, we'll call it centimeters cubed, cubic centimeters. Watch what happens if I drag it up further. The height is now 4. Pi times the radius squared times 4. As I continue to drag this higher and higher, notice the circle doesn't change. The pi times the radius squared doesn't change. All that changes is the height. I'm going to zoom out and try this now with a different, we can move it around too, which is sometimes helpful, right, to get different viewpoints of this. Let's drag our radius out a little bit wider. Notice our diameter is now 16, making our radius 8. Pi times 8 squared times 2. And again, as we drag it up, the circle just keeps on filling in more and more up and down. So I think this is a nice tool to help you see what that's like, right? And why you just keep multiplying by that height. So the volume of a cylinder, just like with a prism, can be found by multiplying the area of the base times the height. Now we know that in any cylinder, the base is going to be found as the area of the circle, which is pi r squared, and then times the height. So again, volume of a cylinder is the area of a base times the height, and we know that specific area of the base is a circle, so it's always going to be pi times the radius squared times the height of that cylinder. So what about the surface area of a cylinder? Think about the outside, again, of this box, right? If I just wanted to measure all the flat space on this box. Well, let's think about how a cylinder could be made. And one way you can illustrate this is actually with a sheet of paper. What happens if I take this sheet of paper and I roll it into a circle on the ends? Doesn't this sort of resemble a cylinder? Yeah. What does it have on the ends? It has circles. It has circles which, again, if we imagine these being closed, surface area is how much total space we have. On the sides, it's this paper, and on the ends, it would be the areas of those circles. Now, the nice thing about when you use a paper is you can unroll this, right? This paper right here is the area of the sides of my cylinder. So if I could somehow calculate that, I can add it to the two circles on either end to calculate that surface area. Well, how do you calculate the area of a rectangle? The length times the width. In a cylinder, if I roll this again, the width of that piece of paper is just the height of my cylinder. But what is the width of it then? Isn't that going to be the circumference of my circle? The circumference of your circle is the same as the length of the sheet of paper. So how can we use that to then calculate the surface area of a cylinder? Here's another little drawing that illustrates this, okay? And so if we want to calculate the surface area of a cylinder, I'm going to sketch a cylinder like this as best I can. Again, what we need to know is the circumference of the circle and the height. And so the circumference of a circle is calculated by 2 pi r, or pi times the diameter. And then we multiply it by the height. And that is going to tell us all around the outside of that cylinder, right? That's going to tell us this space inside here, all this space in here, which is the wraparound part of our cylinder. So it's going to be the circumference, and then we multiply that circumference by the height. So that's the area of the outside of our cylinder. We then need to calculate the area of the circle, right? We need to calculate the top and we need to calculate the bottom. There are 2 of those. They're both the area of the circle. And so how do we calculate that? Pi r squared. And because there are 2 of them, we'll double it. So the surface area of our cylinder will be calculated from this formula: 2 pi rh plus 2 pi r squared. Again, this part is the rectangle that gets wrapped around, and this part are the 2 circles on the top and the bottom. And we add all of those spaces together. So that's how we calculate the surface area of a cylinder. So let's do a little practice with this. Here is a picture of a can of tennis balls, and it measures 7 centimeters in diameter, which means all the way across, and the height is 20 centimeters. So take a moment and see if you can calculate the volume and the surface area of that can of tennis balls. So let's start by calculating the volume. I'm going to start by calculating the volume of this. And to calculate the volume, we're going to need the area of the circle at the top of the can. So the area of the circle, and once we know that, we will multiply that by the height. So our area is pi r squared, and then we'll multiply that by h. So we have 3.14 times the radius. Now, it said the diameter is 7, which means the radius is 3.5 centimeters. So we'll take 3.5 squared. Once we know that, we'll multiply that by the height. I'm estimating pi to be 3.14 here. So 3.14 times 3.5 squared is 38.465. So this part is 38.465. And the reason I did that all by itself is because we're also going to use that area when we calculate the surface area. So I'm just going to note that that right there is the area of the base. Now, to calculate the volume, we also need to multiply it by the height of 20. So we will take 38.465, we will multiply it by the height of 20, and we get a volume of 769.3 cubic centimeters. So there's a volume of this cylinder. Now, to find the surface area, if you recall, we are going to find the circumference of the circle and multiply it by the height. So we're going to take the circumference times the height. Once we get that, we will then add 2 times the area of the circle. So the circumference, again, is 2 times pi times the radius, and then we'll multiply that by the height. And then our area, remember we actually already calculated that? That was this highlighted number in green. So I'm just going to plug that in right now, 38.465. Again, that's going to take care of both of these ends, okay? Both of these ends of my cylinder. For the first part, will be 2 times 3.14 times that radius of 3.5 times the height of 20. If I calculate that, 2 times 3.14 times 3.5 times 20, we get 439.6. And this is area, so that's going to be centimeters squared. And then we're going to add it to twice the area of each end circle. 38.465 times 2 is 76.93. And we will add centimeters squared. And then we'll add those two things together. Plus 439.6 for a total of 516.53 square centimeters. So note that when you are calculating area, whether it's just area or surface area, it's always going to be in square units. In this case, it's centimeters squared. So let's move on to pyramids. I could not find a good example of a pyramid in my house, anything pyramid shaped. Pyramids have an interesting, I guess, image that goes with them. So this one's a little bit harder to, I guess, derive the formula. But here is what it looks like. So I'm going to take a moment to examine this. What you're going to see here is a cube. So this is a picture of a cube. And that cube has a base that is square. Notice this square at the bottom, E, F, G, H. So we've got that square base. You're going to see that same base right here, E, F, G, H. So that's a nice perfect square at the bottom. And then what was done was a line was drawn from point E all the way up to this top front corner, point C. And the same thing was done from C to F and C to H and C to A. And by doing that, imagine just slicing these three pieces off. We ended up with 3 identical pyramids, each of which had the same base, right? Because each of them has a base that's a square that's part of the side of the cube. And so that's a really interesting fact, which helps us derive how to find the volume of a pyramid. The volume of the cube itself would be calculated by the length times the width times the height, because it's a prism. Length times width times height. But we want to find the volume of the pyramid. And because there are 3 pyramids that are equal that could be constructed from the cube, to find the volume of the pyramid, we multiply this length times width times height times a third. We take a third of that number. So the volume of any pyramid can be found by calculating 1/3 times the area of the base times the height. Now, the one that I demonstrated here had a base that was a perfect square. And so that's why it was length times width. But if you recall, you can also have triangular base pyramids. Those would be calculated the same way by doing the area of the base using the formula for the area of a triangle. So it depends on what shape the base of your pyramid is. When it comes to surface area of a pyramid, you are going to be using some sort of regular polygons, or not regular, but standard polygons, where you're able to calculate the areas of each of the sides. You've got a square or a rectangle on the bottom. You have triangular sides coming up. And so if you're trying to calculate the surface area, it's just the sum of the area of each of those pieces, the area of the base, and then we call these the triangular lateral sides. Lateral meaning on the side. Cones, moving on to cones. So we're mostly going to focus on the volume of a cone. And the way we kind of start this investigation, you'll notice that this has a cone, but it also has this hexagon sort of inscribed in it. Um, a hexagonal-based pyramid is pretty close to a cone. And so when you start to try to figure out and derive the formula to calculate the volume of the cone, it comes from that same idea. Um, and what it turns out is that the volume of a cone, in fact, I actually have let me stop sharing. I have a cone, right? This little fuzzy Christmas tree looking thing. So this one actually surprises a lot of people. Now, if you could take this cone and stick it inside of like a perfect cylindrical glass jar that was the same height, this cone would take up 1/3 of the volume of that cylinder. And so that's the way we calculate the volume of a cone. The same way we would do a cylinder. Remember, we take the area of the base times the height, and then we take that number and just take 1/3 of it, because that fills up just 1/3. Mathematically, when you prove it, you do it by starting with prisms or pyramids with different bases and go from there. So when you're working again with the volume of a cone, this is going to be your formula. You're going to find the area of the base, which, because it's a cone, it'll be circular, pi r squared, times the height, and then you take 1/3 of that value. There is a formula for the surface area of a cone. It's a bit more complex, and it gets into the Pythagorean theorem. So we're not going to get too far into that. I'm not so concerned. But you can see that's a little more complex. This part right in here with the square root of r squared plus h squared does come from that Pythagorean theorem. Finally, let's talk about spheres. So spheres, right? Like a ball, right? So spheres are a ball. And this also is very connected to cylinders. It's always interesting to me how these relationships exist in volumes and even surface areas between different types of figures. And so what you're going to see here is the picture of a perfect sphere resting inside of a cylinder. And one of my favorite mathematicians, Archimedes, discovered this relationship more than 2,500 years ago. And so what Archimedes discovered was that the volume of a sphere is 2/3 the volume of the cylinder, and the surface area of the sphere is 2/3 the surface area of the cylinder. So imagine if you could take a ball and rest it perfectly inside of a cylinder, so they had the same height and the same distance across, and then you say fill that with water to the top of the cylinder, and then you removed the sphere from the cylinder, only 1/3 of the cylinder would be full of water. The sphere takes up 2/3 of the volume of the entire cylinder. That's a really interesting fact. And so that leads us to the formula for the volume of a sphere. When you are calculating the volume of the sphere, it is 4/3 pi r cubed. And the reason that is because 2 pi r cubed is the volume of the cylinder, and we want 2/3 of that. 2/3 times 2 is 4/3. And so the volume of a sphere is 4/3 times pi times the radius. Remember, the radius is the halfway across that circle times that radius cubed. For the surface area, we worked earlier with the surface area of the cylinder. Well, again, it's 2/3 of that. And so the surface area of the sphere, again, of a ball, is interestingly 4 pi r squared. So again, remember pi r squared is the area of the circle, and you multiply that by 4. So if you imagine this sphere right here, this circle that exists across the middle of it, if you can find the area of that circle, that's the pi r squared portion. Multiplying that by 4 is the surface area of the entire sphere, which again, I think is a really interesting relationship that exists. So the last investigation that we're going to do is just one little problem here. So we are going to compare the volume and surface areas of two spheres. So I'm going to put the picture of two spheres here. We could ignore this. All right, so we're just going to compare the volumes and surface areas of these two spheres. So again, using the volume and surface area formulas, go ahead and do those calculations for both of the spheres that you see. Go ahead and pause and try that on your own. So I will calculate volume here and surface area here. So the volume of the sphere, first we'll do sphere number 1, the small one. So the volume is 4/3 pi r cubed, which is 4/3 times 3.14 times the radius, which is 1 centimeter cubed. So if we calculate that, what we end up with here is just 1. We multiply 4/3 times 3.14. And we get approximately, we'll have to round this, about 4 point, we'll just call it 4.2, just to make a nice, somewhat neat number. Cubed, right? Centimeters cubed. If we do this for sphere number 2, what we'll see is that we have 4/3 times 3.14, and this time our radius is 2 centimeters. So we will take 2 cubed. So this is equal to 4/3 times 3.14 times 8. And that is about 33.5 cubic centimeters. And what you might notice here is that if we're just comparing the volumes, the second one is actually 8 times bigger than the first one, even though its radius was only 1 centimeter more. Its diameter was twice as big, right? So it had a diameter of 2. This had a diameter of 4. So this is twice as big across. Its volume is 8 times greater. Why is that? It's because of the fact that we have to cube in the midst of our calculation. Let's examine the surface area and compare them. So our surface area formula is 4 pi r squared. So for sphere 1, 4 pi r squared will be 4 times 3.14 times, again, our radius is 1. So 1 squared, 4 times 3.14 times 1 is 12.56. Surface area is always measured in square units. For sphere number 2, it will be 4 times 3.14 times 2 squared, which is, again, 4 times 3.14, and this time 2 squared is 4. And so we end up with a surface area of 50.24 centimeters squared. So we had a surface area here of 12.56, here of 50.24, and here, this is exactly 4 times greater than this one. Why is that? Notice the volume was 8 times bigger. The surface area was 4 times bigger. Again, it's because what we end up squaring that radius instead of cubing it. That's where that difference comes in. And so we'll just finish by stating that, as students progress through the process of learning this, they start with an idea about what volume and area and surface area, what those things mean. We stay away from formulas at first. We want them to find measures. We want them to build the concepts, the conceptual ideas of what these things represent. But over time, as I mentioned in an earlier video, they construct their own meaning. They construct their own formulas. And so it's essential that, we hold off on teaching formulas until these foundational concepts are really internalized.